The Jetson Thor is NVIDIA's new developer kit, and the DGX Spark is for everybody. But what's not often talked about is that Thor has 128 gigs of RAM, just like the Spark. That's a lot of RAM, and it's more than $1,000 cheaper than the Spark. So why don't we just buy the Thor instead of the Spark? Well, you could. I'm gonna run some tests right now to see what it's capable of and talk about a couple of differences between those two machines and also Apple Silicon. The reason I picked these three is because the M4 Pro, the Thor platform, and the Spark all have 273 gigabytes per second memory bandwidth. And I mentioned before many times that memory bandwidth is really important for machine learning, but that doesn't tell the whole story. By the way, NVIDIA sent me this Thor to do some testing, and they're also giving away the Jetson Orin Nano Super, signed by Jensen Huang. Rules for the raffle are in the description. The other two machines I bought. So these days I'm always flipping between models. GPT for research, Claude for coding, Nano Banana for image generation, VO Kling and Runway for video, 6 tabs, 6 bills, and counting. Enter Chat LLM Teams. One dashboard houses every top LLM, and Route LLM picks the right one. GPT Mini for ultra fast answers, Claude Sonnet for coding, Gemini Pro for massive context. They recently added Gemini 3 and GPT 5.1 the moment they dropped. Create professional presentations with graphs, charts, and deep research detailed content. Need human-sounding copy? Humanize rewrites text to defeat AI detectors. Need visuals? Pick frontier or open source models. Nano Banana, Midjourney, Flux for images, Magnific for upscaling, plus VO, WAN, and Sora for video, all built in. You also get Abacus AI Deep Agent to pretty much do anything. Build full-stack apps, websites, reports with just text prompts, and deploy them on the spot. They have Abacus AI Desktop, which is the brand new coding editor and assistant that lets you vibe code and build production-ready apps. And the kicker? It's just $10 a month, less than one premium model. Head over to chatllm.abacus.ai or click the link below to level up with Chat LLM Teams. When it comes to these kinds of machines, an important thing to consider is the amount of power they use. Here I just have the terminal open, NVTop running in the Thor and Spark, and activity monitor running on the Mac. And here is the power usage. Mac Mini M4 Pro is using about 8 watts, the Thor is using about 31 watts, and the Spark is using about 44 watts. That's just to kick things off. I'm gonna run a couple of LLMs here and then do some benchmarking so you get an idea of how these perform. There's a brand new model called Ministro. Haven't tested that on the channel before, so let's start with that one. And I'm using Llama, which is a really dead simple way to get started. I've created tutorials on the channel before on how to start with that and how to set it up. There's really not much to it. Llama run Ministral 3, and I'm gonna give it the verbose flag. Now, different models behave very differently. That's why we have to test as many models as possible. I wish there was a way to keep track of all the different models, all the different versions of them, on all the different hardware that I'm testing, but it's kind of hard to do that. I'm working on something. Design a scalable web application architecture for an e-commerce platform, and so on and so on. This is one of my medium prompts. It gives a really nice long output, really detailed architecture. I have different length prompts that I use. They're all on my GitHub. I'll link to it down below. All right, let's go. And there it goes. That is really interesting that the Mac and the Spark are printing out pretty much the same exact result. They're a little bit different. Now this is gonna be a very, very long result. So while it's happening, take a look at what's going on with the Spark here. There's the GPU usage. We're going at about 95% usage. And over here on the Thor, about 94 to 96% usage as well. But the characteristic of the of the line is very different on these two. The Spark is very even, so it's constantly using 95% of that GPU, but the Thor is bouncing around a little bit, which tells me that just based on the graph, I don't know what's going on the inside there, but it's telling me that things are loading and unloading, loading and unloading at a rapid pace, so it may not be as efficient as the Spark, for example, at this particular task. But we'll see what happens when the result comes. Oh, Spark is done, and so is the Mac Mini. You can see that usage is pretty even there as well. I didn't expect it to finish so soon because I wanted to get the power usage, but I'll get that in a moment. Here are our first results. 39 tokens per second for the generation. This is token generation. We'll get to prompt processing in a bit and prefill. We have 30.82 tokens per second on the Thor and 34.97 tokens per second on the Spark. So they're all kind of close to each other. Well, I guess the Mac Mini won this round and the Thor lost this round, with the Spark coming in right in the middle there. But the token generation speed is not the only story here. Look at the prompt eval rate. That's the prompt processing. This is the part of the process that's not related to memory bandwidth. This is pure computation. And in pure computation, the Mac Mini loses. 353 tokens per second here. The Thor has 1036 tokens per second here, 3 times faster. And the Spark, 2406 tokens per second. So we have very different characteristics on all 3 of these machines. But the 2 NVIDIA machines both have the latest Blackwell chips, which is where that prefill gets processed. So we have the latest Tensor cores in there and the latest CUDA cores. By the way, the Thor has 25% more than the previous generation, which was the AGX Orin. But the Spark definitely beats it out, at least in the prompt prefill stage in the calculation, because it has a lot more Tensor cores and CUDA cores. But that's not the only difference. All 3 of these are ARM-based systems. But just because these 2 are Blackwell system doesn't mean that they have the same exact chip. The Thor has a 4 nanometer process, and that's the CPU part of the chip, whereas the Spark has a 3 nanometer process chip for the CPU, and that's going to directly affect that CPU to GPU communication. So the Spark might be more capable of feeding the GPU part, the Blackwell part, than the Thor. But the Thor is not exactly designed for that particular scenario, as we'll see in a bit. Now, this model is a brand new model, and this is a mixture of experts model, so it's not using all of its parameters that are available at the same time. It's only using a subset of the parameters. It's called a sparse model. If there's a dense model, it has very different characteristics. First, let's run this again because I want to take a look at how much power is being used while all 3 of these are working. So there they are. The GPU is plugging away, doing its thing on all 3 of these. Let's take a look at what's happening with the power. So we're about 70 watts on the Mac Mini. We're about 90 watts here, almost 90 watts on the Thor, and we're at 141 watts on the Spark, which is quite a bit higher. Almost 2 times higher power usage on the Spark, and that's all being used by that compute, that really powerful, fast compute that's on there with more cores. Mac Mini is done. We got 38.95 tokens per second there, 32.92 tokens on the Spark. Just a tiny bit slower, but the prompt eval rate went up here to 2,817 tokens per second, which is ridiculous. And we got 28 tokens per second on the Thor, a little bit slower again, but the prompt eval rate, 1,090. So really good there. Let's take a look at a dense model, which means it's going to be using all the parameters. This is going to be quite a bit slower, but dense models are really good for clustering. And I'm going to go into more of that in later videos, for example, with Sparks over here and Apple Silicon machines. Stay tuned for that. I'm gonna run Llama 3.3 70 billion parameter model, which is a really chunky model. It's over 40 gigabytes on disk, which means it's gonna require all that memory and then some if you want to include some context. So this little Mac Mini is almost all but filled up with its 64 gigabytes of memory there. These machines have plenty more to go with 128 each. All right, here we go. Same prompt, and we got a bigger model now. Boom, boom, boom. Look how much slower this thing is. 70 billion parameters is a lot of parameters. I mean, you got to give it to these little guys. They're small. Look how small they are. It's a 70 billion parameter model. Think about that. This is going to take a while. All right, let's take a look at what's happening here. We've got this GPU usage is pretty steady on the Spark, 96%. We got a similar kind of thing going on the Thor, where the GPU usage is going up and down by a little bit, jumping up and down there. And the Mac Mini has pretty steady GPU usage. But interestingly, it's higher than it was when we were doing the Minstrel 3 model, just by a little bit. So it's using more of the GPU. Memory used on the Mac Mini, 56.87 gigabytes out of the 64, but the memory pressure is nice and clean there, no orange or red, so we're good. Power usage is a bit different here. We got more power usage on the Mac Mini, almost 80. We got more usage on the Thor, almost 100 there, and about the same, or just a tiny bit more on the Spark with 153 watts. Watts is the unit we're talking about here, folks. I know somebody was gonna leave that comment. 53 what? Watt. Oh, I'm hearing some sounds. Who is it? Who is it? The Mac Mini. Can you hear that? It's kind of hard to tell in the video, but trust me, that's what's happening here. The Spark is an extremely quiet machine. Is that good or bad? I don't know. There's other manufacturers like the Dell GB10. That one has a little bit more cooling going on. I have a couple of those that I'm gonna be testing soon, so stay tuned. But yeah, I never heard the Mac Mini make that much squealing before. It's not squealing, it's more like a blowing sound. I gotta say, Llama 3.370B was a good model, but it's getting a little bit long in the tooth compared to some of the smaller models even that are more modern. Look at this. This is supposed to be an architecture prompt. I wanted architecture, but it's giving me code. Not exactly what I wanted. These two are actually giving me architecture. There is a little bit of code and pseudocode, but this one gave me straight up code. It doesn't even know like what technology I want to use. Okay, we've got 5.43 tokens per second here on the Mac Mini. Oh, interesting. 4.61 tokens per second on the Thor and 4.46 tokens per second on the Spark. A little bit of a diminishing returns there on the Spark, even though the prompt eval rate still was amazing on the Spark, more than 2 times faster, almost 3 times faster than anything else. So 283 tokens per second on prompt eval, which is basically prefill. That's the first stage before we do the decode stage, and that's the token generation. If I didn't mention that earlier, my apologies. We got prefill, that's the prompt evaluation, and that could include the whole context. So if you are having a chat session, for example, with one of these things, it's going to include your entire chat session, send that in, process it, everything, including the system prompt too. So you want that to be fast because sometimes the conversations can get pretty long. So good on you, Sparky. We got Thor with 103 tokens per second. Not too bad. Pretty terrible with the Mac Mini, 34 tokens per second. But the M5 generation, hold on to your pants. We'll be taking a look at that shortly as well. The prompt processing on that has improved quite a bit. So 4.46 tokens per second for the Spark. Let's verify these numbers from a different perspective. We're gonna use a tool called Llama Bench, which comes with Llama CPP. And I got the exact same model that I'm gonna be running, but this is the GGUF version. And this gives us both the prefill and the token generation. By the way, I compiled these on the machines. For the 2 NVIDIA machines, I used CUDA compilation. That's why it's detecting the CUDA devices. For here, device 0, NVIDIA Thor, and here we got device 0, NVIDIA GB10. GB10 is basically the platform for Spark, for the Dell, for the Asus machines. And since the creator of Llama CPP actually uses a Mac, you just run the basic build on the Mac and it automatically compiles for it. Now take a look at this. On the Mac, Llama Bench is actually utilizing more GPU than when we were running Llama, just by a tiny bit. You can kind of visually see it. I don't have any concrete numbers here, but maybe we'll see some when we actually see the final results here. Llama might have just a tiny bit of overhead with whatever else is running, the services that it's running. And whoa, look at this. So on the Spark, we got a flat line just like we did before, but here on the Thor, look at that up and down. It's basically shutting down, going to 0 on the GPU usage and going back up to 98%. So more GPU usage, but also less. It's really doing that up and down quite a bit. That was for prefill. That was when we were processing. Now for token generation, it's actually flat. Really interesting results here for that same exact model, the Llama 3.370 billion parameter. Q4KM, by the way, is the quantization. Same one I used with Llama. And Q4 just means it's quantized down from the original, which was probably BF16 if I'm not mistaken, but you'll probably correct me in the comments. Down to int 4, so integer 4, which means it's 4 times smaller, requiring less memory to run. Still, 42 gigabytes is a pretty significant chunk, which means you won't be able to run it on even like a 5090 with just 32 gigs of VRAM. Okay, the Spark gave us a result that's pretty much the same as what Llama gave us. 4.56 tokens per second for TG128. TG128 just means token generation. And we got about 283 tokens per second for PP512, which is prompt processing or prefill. On the Thor, it's not done yet. So wait for that one. On the Mac Mini, 42, which is higher for prompt processing, 512, and 5.48 for token generation. Thor has slightly higher PP 512, prompt processing 130 tokens per second, and TG 128 token generation at 4.4. So about the same there. But the Mac Mini is faster at token generation in this case. This is a dense model. Let's take a look at a sparse model that's pretty popular, GPT OSS 20B. Let's just do 120B because why not? It's a mixture of experts models, so it should be much faster than Llama 70B, but I am a little bit worried about the amount of memory that's available on the Mac Mini because this is a pretty big model. So let's see. Oh, failed to load the model on the Mac Mini. Oh, that's too bad. You can see where having 128 gigs of memory is a big plus here. The two NVIDIA boxes have that, and they're still running it. And here, a pretty big difference between the Thor and the Spark is finally revealed. In this particular architecture, for this particular model, we have more than 2 times faster speed for prompt processing on the Spark than the Thor, and almost 2 times faster token generation speed as well. So the Thor, 37.17 for token generation, 464 for prompt processing, while the Spark has 52.77 token generation, 977 for prompt processing. Pretty big difference there. As you can see, the type of model and the architecture of the model that you're running matters a lot. But let's say you're running a dense model and you want to save some money. The Thor is not a bad option. 128 gigs. But generally, the Thor is meant for applications like automotive, robotics. It's supposed to have deterministic latency, which means it doesn't vary its performance as widely as Spark does. I didn't test the variability between different things. I just showed you examples, but theoretically, that's what it's supposed to be good at. So safety first, power conservative. We saw that it uses a lot less power than the Spark, and the Spark would be better for bursty kind of applications and serving multiple users. Now we took a look at Llama CPP. On the CUDA platform, you have VLLM, which is really good at serving multiple users at the same time and doing concurrent tasks. I haven't showed you it in this case, but I did make a video about that. You can watch that right over here. Thanks for watching, and I'll see you in the next one.